so far, we've seen how an alcohol can be produced by a simple substitution of a suitable leaving group, such as the reaction shown here. In cases like this, the OH of the alcohol ends up on the same carbon where the leaving group was initially attached, okay? Under neutral or basic conditions, an oxirane, which is an epoxide, it's the simplest epoxide that we have, and an epoxide is just this kind of ring structure with an oxygen bond, can also react with a nucleophile to form an alcohol. Now, we've got two equations here. These are under different conditions. So this is under neutral conditions, and then this is under basic conditions. In both cases, the OH and the nucleophile end up on adjacent carbon atoms in the product. So when you're looking at this, sometimes initially it kind of gets wickedy wild. This has two carbon atoms right here. Here are the two carbon atoms here, two carbon atoms here, here are the two carbon atoms here, okay? And so that's what we mean by adjacent carbon atoms, just as we're kind of looking at this. So we're going to dig into these neutral and basic conditions in this section. Just as a brief aside, one of the things you're going to notice is here's 2-methoxyethanol. 2-methoxyethanol is really helpful because it can dissolve a wide variety of compounds, including grease and oils. And so it's a multi-purpose cleaner. So it's in a lot of multi-purpose cleaners. It's also used as an additive in airplane de-icing solutions. So this is a really robust way to make it. So let's look at the epoxide mechanism. Now, in the epoxide mechanism, and we're going to start out with our friendly epoxide here. And we are going to use, we're going to go ahead and use the basic conditions, right? So this is an epoxide mechanism. It's a strong nucleophile. Under basic conditions. And this is the mechanism for equation 1044 on the previous slide. I can't go back or it'll break up, but you can go back and look, and this is going to be the mechanism for that. So in the first step, we have CH3O minus. Now, when you go back and look at that, you're going to see that that's listed as NaOCH3. But remember, Na is a spectator ion, so we can get rid of that. So the first thing that happens is the epoxide is attacked by the nucleophile in an SN2 step. And so just like kind of before when we talk about this, this is got a negative charge. CH3O minus has a negative charge. So that's very electron rich. And what we need to do in the epoxide ring is identify what's really electron rich. Well, we know, or electron poor. We know that this oxygen here is very electronegative. And so it's going to pull away the electrons from the two carbons. And it makes both of these partially positive. And so we know that negatives and positives like each other. So here we have this negative charge, and it's either going to attack here or here. It doesn't matter which one you choose because this is symmetric. Now we're going to talk about things that aren't symmetric in a second, but for right now it doesn't matter. So we're going to come in here, and we are going to, the epoxide here, these electrons are going to attack one of the partially positive carbons, okay? Now, when that occurs, the electrons that make up the bond between the carbon and oxygen will break. That bond will break, and these electrons will go on the oxygen. The reason that this bond breaks is because this bond is weaker because this oxygen is withdrawing electron density. So there's a lot more electrons closer here. So this is a weaker bond. That's the one that breaks. Electrons are shared pretty evenly between this bond, the two carbons, so you're not going to see that break. So this one breaks, and those electrons go here. Now, when this happens, I've always told you, follow your arrows because that shows you where your bonds are going to go, right? And so we know we're going to have a new bond between the CH3O and that carbon. But what happens here is this opens up like a door and kind of flops over this way. And so our product, so here's how I draw this. This is an SN2 reaction. So I start out and I say, okay, great. I have, I'm going to draw it as H3CO. And I'm going to draw my bond to the first carbon, the second carbon, and then I draw a bond to the oxygen. Negative like that. Now I'm going to highlight the carbons again so you can kind of see, right? Here are those carbons, and then here are those carbons there. Okay, so you can see those are the two carbons, and you can see how the oxygen opens up. Now, very quickly, because we have a negative charge here, this is in a basic environment, so it can undergo an acid-base reaction very quickly. It's going to go through a proton transfer. It'd be helpful if I went back to that. So we're going to have a proton transfer where the conjugate acid of the base that we used comes back in. You'll notice over the arrow on the previous slide that it showed NaOCH3, and then it shows CH3OH. These two, when we look at them, right, it's OCH3 and CH3OH. These are conjugate acid-base pairs. Most of the time when you do a reaction like this, you choose your solvent to be the conjugate acid or the conjugate base of what you're using. It helps reduce any byproducts that you have. Okay, so these electrons come here, they steal the proton, these electrons go on the oxygen, and now we have our product. Okay, the reason that this happens and that epoxides can do this is because they have a lot of ring strain. So epoxides can undergo SN2 reactions because it relieves their ring strain. Right? Now, when we talk about this, we mentioned that this is completely symmetric. And so the burning question in your heart, I'm sure, is what do you do if the epoxide has alkyl groups that are different, that are attached to the carbon atoms in the ring? And so let's look at this. We have an example here, okay, where the carbon atoms that are here are what we call non-equivalent. They're also both chiral centers. And so what happens here is when we react this again with a base, so that's a base, and this is a sequential, it's a sequential reaction. So we have a base and then an acid workup. What you're going to see is that preferentially this base adds to this side right here. Okay, this is the only product that you get. And so what we can say then is under neutral or basic conditions, a nucleophile attacks an epoxide at the less highly alkyl substituted carbon atom of the ring. Substituted carbon atom of the ring from the side opposite the oxygen atom. Okay, so what we see here in equation 1046, right, is that we are gonna have This one is the least substituted. We'll do that in green. This one's the least substituted here. And so that's where the attack's going to be. Some of the reasons for this, one, the rate is highly sensitive to steric hindrance. There's just too much going on the other side, right? It's an SN2 reaction, right? And then the nucleophile must attack from the side opposite the leaving group. And in this case, that leaving group is the oxygen, right? Even though it doesn't leave the molecule, it leaves the bond, okay? So what that means here is when it attacks here, you're going to see something like an inversion of stereochemistry where this bond gets pushed up, okay? And you're going to notice that these two here keep their stereochemistry, right? But this does get pushed up. So let's look at the mechanism for this. So we're doing the mechanism for the previous reaction. So we're going to have our base here. Right here. Okay, so what happens here is it undergoes a backside attack, so on the other side of the oxygen. Now, this leads to something called a Walden inversion. And honestly, in most other books, one of the reasons I paused briefly on the previous slide, in most other books, it's going to show that this goes from a dash to a wedge instead of just rotating it up. But this book shows that it rotates up. I don't particularly love that, but it's good for you to be able to recognize both of those. My favorite is showing it like truly changing. Instead of just rotating up. Okay, so that's our SN2 step. We're going to go through a proton transfer. Right. Since it's an acid workup, that was that second step. We're going to use the H30 plus. And these electrons are going to come in and grab that proton. And those electrons are going to go on the oxygen. And then we end up with CH3, CH2O, boop. Let's not be lazy drawing our bonds there, okay? So the attack occurs at the least substituted site because there's less steric hindrance, and then it leads to a Walden inversion. And basically the remaining groups attach to that carbon flip upwards. If you don't show them flipped upwards, what it will look like in a lot of books, we'll show it like that, right? So this book just shows that it's kind of pushed up instead of rotating it around. But I want you to be able to see kind of both of those. So an example, okay? Predict the major product of the following reaction. Pay attention to stereochemistry. So we look here at this reaction and we say, okay, hey, look, the first thing we need to evaluate is we have an epoxide ring. So far, we've only done one reaction with an epoxide ring, but you're going to learn a second reaction. So you need to evaluate whether this is an acidic or basic. And so you need to look at the very first reaction here to do that, because this in the second step is just a generic acid workup. And that's to help facilitate that proton transfer. So when we talk about this generic acid workup, it can be shown in a lot of different ways. It can be H3O plus, or it could be another acid that's shown there. So what you have to do is you have to ask yourself, hey, look, is this an acid or a base? Generally, if you've got an acid workup step, that's going to be a base, okay? And so when we look at this, though, we know that OCH2CH3, right, it's got a negative charge on it, but we also realize that that is a base, right? And that's a strong nucleophile. So this is under basic conditions. We have a strong nucleophile here. The nucleophile, I left out 2 electrons there. Don't be me. Make sure all your electrons are there. CH2, CH3. Okay? So that's electron rich. It acts as the nucleophile. Which carbon atom of the epoxide ring will the nucleophile attack? We're under basic conditions, so it will attack the less sterically hindered. Okay, carbon of the epoxide ring, which is the one right here, right to the left. Then, from what direction relative to the epoxide oxygen must the nucleophile attack? How does that impact the stereochemistry? So the nucleophile attacks from the opposite side of the ring, like below the ring, the opposite side of the oxygen. So that remaining substituent attached to the carbon flips forward. So the acid then, of course, protonates the OH. So if we were just predicting the product for this, we could use this information to just predict the product. And we could say, okay, it's going to attack there. That ring is going to open up. It's going to push up that CH3 group. This is going to attack here. I don't love the way I've drawn those bonds, so let me erase those. Because we want to be really careful. We want that bond to go up here. Right, there we are. We know that that oxygen gets opened up and protonated, and then this stereochemistry stays the same. Okay, so it gets rotated up. But this problem is not only saying predict the major product. Oh, it just says predict the major product of the following reaction. Pay attention to stereochemistry. But you know what? In our hearts, we're going to go one step further, and we're going to show that mechanism, because mechanism practice is very important. Sure, you're practicing your mechanisms. And you could even pause me here, right, and see if you can predict this mechanism and then restart the screencast and check. So let's jump in here. So we've already talked about it's going to attack from under here. The carbon-oxygen bond breaks because it's the weakest, and those electrons go up on the oxygen. That is an SN2 reaction, and it forms CH3, CH2O, with another CH3 group there that's been pushed up. O. Just like that. Don't forget your minus charge there. We want to show all our charges. We've got an acid workup. So that's H3O plus. Those electrons come in, those electrons go there. That's a proton transfer. And now you have our friendly product. Okay, so make sure you're practicing the mechanisms. Practice makes perfect. And my suggestion is just to write mechanisms over and over until you can do the mechanisms without looking at your notes. So we have talked pretty in depth about how epoxide ring opening happens in basic conditions. Let's flip over now and talk a little bit about some of these acidic conditions, right? So when we look at acidic conditions, you're going to notice that these two carbons here are not equivalent. And what you're going to notice is under acidic conditions, and this is what acidic conditions look like. Notice we just have concentrated HBr, generally things like water are our solvent, right? And what we see happen here, right, is that the Br attacks the more highly substituted side. So basically we end up with the opposite product of what we saw with a base condition. So under acidic conditions, the nucleophile attacks the epoxide at the more highly alkyl substituted carbon atom, okay? So when we have a difference in this, we say that we have different regiochemistry from the neutral or basic conditions, okay? So when you change conditions and you have a different product formed, we say that's regiochemistry. So under acidic conditions, the nucleophile attacks the epoxide at the more highly substituted carbon. Okay, so let's look at that mechanism. All right, so we're here under acidic conditions. We have our friendly epoxide here. We have HBr here. These electrons are gonna, oh, I've left off a group. These electrons are gonna come out and attack that hydrogen and get that proton. Those electrons are gonna go back on the bromine. And so here we start with a proton transfer, right? So then what happens is we have an oxygen here with a hydrogen with a positive charge. And then we have our group here. Now, that positive charge, I want to choose a different color, okay? The positive charge on the oxygen makes there be a weaker bond to the oxygen from the more substituted group. So the positive charge on oxygen results in a weaker bond, right, to the oxygen from the more substituted group. So what that means is that this is going to have a much bigger partial positive than this guy over here, okay? And so that larger partial positive, when the bromine comes in, right, it attacks right here and that opens, okay? And so that's an SN2. And there's your product. I want you to make a few more notes about kind of this, why this is happening, okay? The additional alkyl group on the carbon atom is electron donating, and it helps stabilize that large partial positive charge. Okay, so that carbon-oxygen bond, as we've already mentioned, is on the more highly alkyl substitute carbon is just broken to a greater extent, and we're going to look at that more on the next slide. So let's look at some bond links. So maybe you're like, well, Dr. Pierce, this is all great and good and all, but how do scientists really know? Well, we really know by using experimental data, right? And so one of the experimental pieces of data that we can use is we can measure bond lengths. And so when we look at this particular oxirane, we see that these bond lengths are 143 picometers. What happens when this oxygen has a positive charge is that this bond length goes to about 160 picometers. This one is 151 picometers. So this is a longer and weaker bond to the more highly alkyl substituted. So it makes sense then when the nucleophile approaches here, because we've got this large partial positive charge, that it's going to open up this way, right? So that's a way to visualize what we're seeing. If you're interested in this, there's a lot of research and estimation of bond lengths. And that a lot of times shows up in physical chemistry labs or what are called physical organic chemistry labs, where they look at bond lengths to see what the mechanisms are. Which is kind of interesting. It's an interesting subgroup of chemistry. And if that's something you're interested in, let's talk later about that. All right, so we've talked a lot about how valuable epoxides are as substrates in nucleophilic substitution reactions. But maybe the burning question in your heart is, hey, Dr. Pierce, how do those suckers form? Well, epoxides are pretty unstable because they're super reactive. So epoxides, very unfortunately, can form accidentally and cause explosions. We'll talk about that more in class, accidental epoxide formations, but it's why if you find an old bottle of ethyl ether that's ever been it's been opened and it's older than 3 months, you have to call the bomb squad to come get it, right? Citric acid is another one that sometimes if there's a metal cap, you have to call the bomb squad, those types of things. So, and it's all because these form peroxides and epoxides and those types of things, and they're very reactive, which means they're very unstable. But so what are some good ways to form these? One way to form an epoxide is from something called a halohydrin. Now, a halohydrin is shown here. A halohydrin just has a OH group that is on an adjacent carbon from a from a alkyl, halogen. Oh, all the words, right? From the halogen there. So let's look at the mechanism for how this forms. Now I want you to notice I am not being a lazy chemist. I'm not doing the first step of the mechanism, right, with what's written there. I'm rewriting my starting products here to start the mechanism. And that's really what you need to strive to do. You need to rewrite these because I can really show the bond here, right? And show very clearly what's happening to the electrons and where the electrons are moving. You can't show that very clearly here. So you need to rewrite your starting products there. So the first step is going to be a proton transfer. We're in basic solution. So we lose that Na as a spectator ion. So we have OH minus, right? And so it's a proton transfer. So it's going to come in, it's going to steal that proton. Those electrons that make up the bond between the oxygen and hydrogen are going to go over there to the oxygen. We follow our arrows and now I've just shown the CL a little bit differently just to kind of help with my arrows, but you could obviously show it pointing up if you wanted to, right? And what we're going to find here is a intermolecular reaction where the oxygen here is going to come down and attack this carbon next to the chlorine. Now this makes sense to us. Chlorine is very electronegative. That makes this carbon more electropositive. Oxygen's negative here. We know negatives and positives like each other, right? So it kind of forms a new bond between these molecules. Now when it does this, it bumps off the chlorine. So this is an SN2 reaction. And so we get that epoxide there. And so that's the mechanism. Now in a previous section, previously in chapter 9, we learned that intramolecular cyclization reactions are favored when 5 and 6 membered rings are formed. So maybe you're like, why does this reaction form a strained 3-membered ring then? Well, it has to do with the location of the nucleophilic oxygen relative to the leaving group. All SN2 reactions require the nucleophile to attack from a side opposite the leaving group. And so because this bond can rotate 360, when the oxygen and the chlorine, which I've shown here, are anti to each other, remember that just means they're on the opposite sides of the bond, then that O- is perfectly situated to carry out that backside attack. And so that's why this occurs. So in these two sections, we have talked about epoxide mechanisms and how to form epoxides. And in the next sections, we will look at diazomethane formations of methyl esters.